Hello everyone, welcome to the video on Vanishing and Exploding Gradients by Society of Artificial Intelligence or SOAI. I am Ritul and these slides are created by my colleague Tushar. Let's start. Vanishing and Exploding Gradients, Revisiting Gradients. This particular video focuses on revisiting how the generic formula for the loss function in context of RNNs is derived. The above formula was derived as we had multiple paths leading to W from L, which means we will have to summate all those previous states to compute the gradients with respect to W. As we know, each of the subsequent states St depends on all the previous states St-1, St-2 to S1. Taking in consideration all these states, we can simply write the term in read as we can simply the equation as del Lt of theta by del W is equal to del Lt of theta by del St multiplied with summation from k is equal to 1 to t del St divided by del Sk del multiplied with del Sk by del W. Note: the k plus 1 here in the product statement shows that we have a total of t minus k plus 1 elements. Zooming into one element of the chain rule. This is part 1. Some key points till now. If the difference between t and k is very large, the product would have many recurrent gradient terms. We can observe that every pre-activation Aj is a function of the sigmoid of the previous state, whereas the activated state Sj depends on the pre-activation state of current time stamp only. Aj is equal to big U xj plus big W sj minus 1 plus b, and sj is equal to sigma of aj. Based on the statement above, we can simplify one of the factors as del sj by del sj minus 1 is equal to del sj by del aj multiplied with del aj by del sj minus 1. As both of the gradients Sj and Aj are vectors of size R of part D, it can be stated that the quantity Dsj by Daj will be a resultant matrix of size R with part T and D. So now, talking about one of our previous conclusions that each post-activation state Sj depends only on its corresponding pre-activation state Aj, we can assert that the rest of the terms except the diagonal in the matrix Dsj by Daj will become 0. Thus the updated form of the matrix will be you can see on the screen, which can also be written as a simple vector of size R with part D, which is diagonal of sigma dash of Aj. Now zooming into one element of the chain rule, part 2. If we take a look at the other element of the chain rule, that is daj by dsj minus 1, we can simply say that it would be a sum of the derivative of three terms in aj with respect to sj minus 1 as shown below. As the terms uxj and b are independent of si minus 1, the gradient of these terms would also become 0. So now we can say that aj is equal to uxj plus w sj minus 1 plus b. The gradient of the second term, which is left to be non-zero, can simply be stated as w. Taking in consideration a second perspective, we can see that daj by dsj minus 1 will be of size r, d and d, and so is the matrix w. So we can write the whole elements which was earlier divided into two products be like aj becomes wsj minus 1. According to our update rule in gradient descent algorithm, the problem of vanishing gradients occurs when the update terms is too small, that the change would be too small. On the other hand, exploding gradients is the problem that occurs whenever the update run is so large that the update lets it overshoots the minimum. Now, vanishing and exploding gradients are small detour to calculus. Now, if we want to know that what would be the magnitude of the given term, let's have a look at the basic calculus. If we want to minimize or maximize a function with respect to x, that is, we want to find the value of x such that the first derivative of function converges down to 0. If we want to know whether the particular value of x gives us the minimum and maximum value for that particular function, we need to compute the second order derivative of the same function. If the second order derivative of that function is positive, the value of x for which the first derivative is 0. Example, let f of x is x square plus 2x. Example, let f of x is x square plus 2x. Putting df of x by dx 0, we get x is equal to minus 1. To know whether the function will be taking either the maximum or the minimum value at x is equal to minus 1, we will have to check whether the second order derivative d square f of x by dx square will be positive or negative quantity, as d square f of x by dx square is equal to 2 is a positive value. We can say that the value of function f of x at x is minus 1 is minimum. Looking at the magnitude of the derivative, according to Cauchy-Schwarz inequality theorem, we can state the following. Note, refer to the following link for a proof when we particularly talk about the sigmoid nonlinearity, as we have seen in the lecture that it takes the maximum value for the function x multiplied with 1 minus at x is equal to 1 by 2. When we talk about RNNs, 10H nonlinearity is often being used and the maximum value for the function 1 minus x square is at x is equal to 0. Now that the function values for both the functions are, you can see on the screen, arriving at a specific term. As per the concept, we know what vanishing and exploding gradient actually means. If we take a look at the earlier derived product, which consists of several similar derivatives. So, if the value for gamma multiplied with lambda is smaller than 1 and t minus k is very large, the resultant would be a really smaller quantity, which will be termed as a vanishing gradients problem. Similarly, if the resultant value is larger enough, the problem here would be exploding gradients. Society of Artificial Intelligence, thank you.